This is Math 1151, and you guys have chosen to come to class after a very difficult exam. Congratulations, very good. Well, what we're going to talk about today is the fundamental theorem of calculus. This is the thing that, if there's one thing that you should learn in calculus, it's the thing we're teaching you today. Derivatives are the other one thing you should learn in calculus, right? But this is the fundamental theorem, right? So, and before we start, remember what a definite integral. So remember this. This is the big fact. Definite integrals compute signed area. Now I'm going to introduce something that I've been wanting to introduce for a few lessons so far. It's called the accumulation function. And here it is. It's the integral. And what you do is you pick, we're going to do it for a real, we're going to do a real example, so a quasi-real example. X, Y. Here. That could be 3 right there. It's the integral from 3 to x of f of x dx. This is the accumulation function, and we'll use a capital F for it. And so what this does is it calculates accumulated area. This one, in this case, it's after 3. And so as we move to the right, what happens as we move to the right? What happens to f of x? It's going to calculate this area. What's f of x going to be do? What's capital F? What's capital F? What's this equal to? Can somebody tell me what that's equal to? It's equal to 0 because when we're at 3, we've accumulated no area, right? Capital F of 3 equals 0. F of 4, just tell me, is it positive or negative? It's positive. How about f of 2? What's f of 2 going to be? It's going to go, f of 2 is going to go the other way. Right? So that's going to be the integral from 3 to 2 of f of x dx, right? And it's going to be, when you go the other way, when you switch, when you're going from larger to smaller, it makes the area the opposite sign. So this is negative here. Negative. It's negative. And as we go from as we go from 2 to 4, capital F is it increasing or is it decreasing as we go from 2 to 4? It's increasing. It's increasing. It's increasing. And what do we know about lowercase f? And lowercase f is, what can you tell me about lowercase f? From 2 to 4, it's positive, right? It's positive. That's a good question. This is a graph of lowercase f. Lowercase f is positive. Let's do one more example. I'll put 1 here. We're going to do another accumulation function. Here we go. This is lowercase f. So now, capital F of x is equal to the integral of 1 to x, lowercase f of x. Oh, geez. Oh, no. Bart, what are you doing? Okay, put a t here because, put a t here. I should have, why am I having such a brain fartish day? Okay, there, t. Well, here's the deal. X is the variable here, and t is some sort of placeholder. We don't want you getting the placeholder and the thing that's changing confused. And so really the best way to denote this is you put a t here, and then we say, okay, and now x is someplace here, and then the area that you've measured is this much. Okay, so capital F of 1, what's capital F of 1? 0, because you haven't accumulated. This is, and then here's 1. So we've accumulated. Capital F of 1 is 0. Now, if I do capital F of, say, 1.2, what's happened? How much area have I accumulated? I've accumulated negative area, right? So our function is negative, right? So we're accumulating negative area. Function is we're computing the integral from 1 to 1.2 of f of t dt, and we're computing negative area. And then at some point here, these are going to cancel, aren't they? These are going to cancel. And so we're going to get 0 area again. And so at some point, so f of, let's pretend, what could this be? This could be 2 maybe. That could be 2. Do you guys agree with that? So maybe f of 2, which is equal to the integral of 1 to 2 of f of t dt. This is maybe equal to 0 again. So look, I have a function that goes from 0, then it's negative, and then it's 0 again. What does that mean that this thing does? It goes from 0, it's decreasing, and then it's increasing. Now look, let's think about this for a second. It's negative here. It starts off at 0, and then it's negative and getting more negative, right? So as we're going here, it's decreasing, it's decreasing, it's decreasing, it's decreasing, it's decreasing. And then what's happening here? It starts to change. Now it's increasing, it's increasing. It's still negative, but it's increasing, increasing, increasing. And then at some point it's 0. Look, it's decreasing. Capital F of x is decreasing when lowercase f of x is negative. Capital F of x is increasing when lowercase f of x is positive. What does this remind you of? Hopefully it reminds you of something. If it doesn't, that's okay. It's a long shot. Derivatives, right? Yeah. So here's the deal. The fundamental theorem of calculus says that if we would happen to guess, you can actually even explain why the concavity works. If you would guess that this thing is the derivative of this thing, then you are correct. And so let's write that down as the fundamental theorem of calculus. So here it is, fundamental theorem of calculus. So f of x is continuous, and capital F of x equals the integral from a to x of f of t dt. And remember, this is just because we don't want to get our input variables and our placeholder variables confused. Then f prime of x is equal to f of x. The reason this is the fundamental theorem of calculus is because we're taking the idea of the derivative. The derivative computes what's the derivative compute again? Slope of the tangent line. And integrals compute area. Why should the slope of the tangent line have anything to do with area under a curve? Who knows? Well, I mean, actually, this kind of explains it a little bit. The fundamental theorem of calculus says those two things are connected in exactly this way. And so somebody asked me, are we going to find an easier way to compute these integrals? Absolutely. What we're going to do is we're going to do it by undoing derivatives. That's how we'll compute the areas that we were doing those horrible Riemann sums for before. So there's a version 2 of the fundamental theorem of calculus. And it says this. F of x is continuous, version 2. And this is version 1. If f of x is continuous and capital F of x is any antiderivative of f of x, then the integral from a to b of f of x dx is equal to capital F of x evaluated from a to b. And this thing here means f of b minus f of a. That's good enough. Okay, so we can see the fundamental theorem. This is the easier one to see. If you draw an accumulation function, you could probably convince yourself that this should be the derivative. This one gives a method for computing the signed area that we didn't have before. That's the difference. So let's see some examples of this in action. Here we go. So we computed this Riemann sum several times, the assigned area between -1 and 1 of x squared. The question is, how do we compute this? Well, what we have to do is we got to find the functions whose derivative is x squared. And what's the answer to that? Yeah, what's up? These are okay to be x's. The issue here was, he says, are these supposed to be x's or t's, right? Because before you got all freaked out for some reason, right? And the reason I got all freaked out before is because I had an x here. And I didn't like having x here and x here. It's not really wrong even. It's just confusing. This is the thing that's labeling the axis, and this is the number you're plugging in. Otherwise, you end up playing a game of like the who's on first, where who's is somebody's name and who is also a question word. That's the issue. So the one variable is playing sort of the placeholder and the other variables playing a number. Because there's no x's here, I don't have the problem. I can go ahead and use x. That's the issue. Okay, so what's this computing? Let's just draw a quick picture. Just to remember, it's very easy. You guys probably all know. So here I have my graph. And of course, I'm using all the wrong colors, but it's OK. There we go. There. It's computing that shaded area right there. It's what's supposed to be computing. Now, what's the antiderivative of x squared? Whose derivative is x squared? Right, x cubed over 3. And so what you often write is x cubed over 3. And you make a big, long vertical line, like so. And then you put that number there, here, and that number there. Yes, yes. He says, do we just ignore C altogether? I'll take care of that in just 1 second. For now, yes. And for later, essentially yes. Okay? Because what's this going to mean is, what you do is you say, well, this is 1 cubed over 3 minus, it's the top minus the bottom. The top minus the bottom minus negative 1 cubed over 3. Stop right there. That's where you can stop if you want to. That's where I advise you to stop. I suggest you stop here. I'm not going to. So now, this is negative 1, so this is 2/3. This guy says, what happened to the C? Good question. Okay, wait. Everybody, get this in your notes. And then what I'm about to write down, don't write down. There's no point to it, okay? But it's good to say it anyways. It's good for you to know. Everybody ready? Let's do it. So suppose we wrote down another antiderivative, plus 6 from negative 1 to 1. That's another antiderivative. It's just as good as the first. When I do this little subtraction dance here, that's going to be plus 6 minus this plus 6. The minus sign will distribute, and the 6's will cancel, and you'll get your same answer. All right? So she says, so essentially you don't have to worry about constants. Like I said earlier, you basically don't have to worry about constants. Now, there is a time when you do, and the time that you do, can you guys tell me when you need to worry about constants? When there's no limits given. So, if we say f of x dx, nothing here, right? That's equal to f of x plus c. When I become powerful in the calculus community, maybe I can change that you have to do that, okay? Because it's not really that big a deal. I don't think anybody here would forget that. I think if I was sitting next to any of you and you were able to compute the antiderivative correctly, and then I just poke you really hard, you'd write plus c. Okay? I think that's true. What I'm more afraid of, actually, is I'm afraid you guys will get this confused. It's top minus bottom. Top minus bottom, right? And if you actually compute the number, you can always tell if you're right by plotting it and seeing, oh, should I be positive or negative? Because if you bottom minus top, it will give you the other answer. Don't mess up that, okay? That's serious. But you know what we like to ask you on exams? Oh, God, calculators are really screwing up the calculus curriculum because some calculators, I think yours can, I don't know, can compute definite integrals for you and tell you the answer, if you haven't nodding yet, and just give you the number. And so to avoid that problem, we started asking you this question, right? Where you have to put in the plus c. Oh, God. Okay, so yes. Anyhow, anyways, yes, okay. If you have questions about that, I'll be happy to try to clarify more. Good, I have my audio on. Are we ready to try another problem? Yeah. Let's do it. The bad news is integrals are hard. Oh yeah, I'm supposed to give you good news at this point. Yeah, shoot. What? What? Semester's almost over! We only have like this in a week. I am so excited! Aren't you guys excited? I am super excited. Okay, so let's do this integral. Here we go. The integral from 1 to 2 of x to the 9th plus 1 over x dx. Fantastic. All right, remember, this is computing signed area. Because this is computing signed area, well, when you add these together, they're like stacked on top of each other. So you can separate these things. You can say, well, this is equal to, although you don't have to, x to the 9th dx plus the integral of 1 over x from 1 to 2 dx. By the way, most fundamental question that we can ask in mathematics is, what sort of thing is this? What is this? What type of answer is this? It's a number. It's a number, right? What type of answer does this thing give? A function. What type of answer does a derivative give? A function. That's right. These are talking about the types. And like if somebody's asked, I'm supposed to quiz somebody and I want to be super nice, all I do is I ask them about types. Say, what is this thing? Is it a number? Is it something else? Okay, so now, how do we do this? We've got to take the antiderivative. What's the antiderivative of x to the 9th power? Good. This is x to the 10th over 10 evaluated. It said evaluated from 1 to 2 minus, what's this thing here? Fantastic. Natural log of x evaluated from 1 to 2, right? Oh, it's plus. So now, this is going to be 2 to the 10th all over 10 minus 1 to the 10th all over 10 plus natural log of 2 minus natural log of 1. Done. If you ask me, definite integrals are the ones with the limits are where it's at. The indefinite ones, I don't know. I think you should leave the answers like that. Unless the question specifically says, give me a number, leave it like that. Especially at the front page of the exam. We had a big argument about this last night when we were grading. Somebody said, we should count off for this. I'm like, no, you can't, because it says here. Okay. Okay, so now let's do another problem. That's not exciting. Here's a problem I don't know how to do. Let's do it. Well, we'll do that one in a second. Okay, here we go. How about the integral from 4 to 9 of 2 over x square root of x dx? I need to start doing, hold on, I'm going to get some harder problems too. So think about that one for just a second. We got to do harder problems. Oh. Okay. How do we do this? First step, simplify. Simplify first. And the first thing I would do is I'd say this is equal to, remember constants can come out, but I don't ever think it doesn't help me do integrals. So I'm just going to leave them in. 2. Now what's this thing here? What is the square root of x? How do we usually deal with it? x to the 1/2. And so this is x times x to the 1/2. So that's x to the 3/2, isn't it? Right? Dx, 4 to 9. And then this thing's equal to 2 times x to the minus 3/2 dx from 4 to 9. And at this point, we should see how to do this problem. We should say, oh, I see what's going on. Right, and so now this is equal to, can we just compute let's try to compute the antiderivative. Let's not think too hard about this, okay? So if you just had to kind of guess what the answer was here, what were we doing before with the exponents? What were we doing? We were adding 1, right? We were adding 1, and so if I add 1 to minus 3/2, I get minus 1/2, don't I? So x to the minus 1/2. And so what you do is you get on the little corner of your piece of paper, you write this down. You write down x to the minus 1/2, right? And now take the derivative of this. And what's the derivative of x to the minus 1/2? d over dx of x to the minus 1/2 is equal to minus 1/2 times x to the minus 3/2, right? Okay, so this isn't so far off from here, right? The problem is this constant term is not what we want it to be, right? So let's just multiply this thing by what we need. And what do I need to multiply this by to get to? Negative 4. That's okay. So I'm gonna multiply this by 4, and so this is equal to minus 4 x to the minus 1/2 evaluated from 4 to 9. Now, suppose you don't know if you're right. How do you check your answer? You just take the derivative. You take the derivative. And so now I'm going to get, this is equal to minus 4, 9x to the minus 1/2, minus a negative 4 to the minus 1/2. Okay? What questions do you guys have about this? You can go pretty far just by knowing this. Okay, let's do a slightly harder problem. Here we go. How are we going to do this one? I was asking people in my other class about stuff like this today. How do we do this? What are some options we have? What? We could rewrite it as piecewise, and that's a fantastic idea. He says, rewrite it piecewise, and what does the absolute value of 2x look like? Yeah, that's right. That's right, it looks like a V. And when we do 2x, oh geez, 2x minus 4, oh, it's going to lower it, right? It's just still going to be centered around the origin, you guys. So it's going to look something, I like the nodding that I'm getting. Okay, there we go. So it looks like that, right? That's what it looks like. So if we're computing this antiderivative, this integral, that's the area we're computing, isn't it? Whoa, Bart. Stop. We're computing from minus 4 to there. We're doing something like that. Right, that's the area we're computing. And so if we do it piecewise, what we really need to do is break this integral into two. Integral from -4 to 0 dx plus the integral from 0 to 1 of, now this one's going to be easy, 2x minus 4 dx. Isn't that right? And what should this one be? Minus 2x? Plus 4, thank you. Is that right? No, wait, minus 2x plus 4? Still minus. Right? The only thing that's negative is what? The slope. The slope. Is the y-intercept still the same? Yes. Yes. This is the answer to that. Okay, so let's do this. What's this going to be right here? What? Oh, it might be 0 from the graph. That's a good idea. Close to 0, but let's go ahead and anti-differentiate it and find out. So, fine, that's a good answer, 0. Let's see if he's right. So it's going to be minus 1x squared minus 4x evaluated from minus 4 to 0 plus x squared minus 4x all in parentheses. When you do this, you have to put parentheses around it. We should invent some better notation. And we have, but we're not using it for some reason. Okay. Uh-oh. What's the deal? Oh, what's this look like? Is this right or is this wrong? So she's saying it looks like this, right? I have no idea what's going on. No. I mean, yes. He says, Bart, the absolute value doesn't look like this. Stupid Bart. He says the absolute value, he says what you graphed is this. Isn't that right? That's right. All right, let's fix it. So how do we fix it? Where does that thing equal 0? When x equals 2, that thing is 0. I'm sorry, guys, cross this out. Stupid absolute values confuse the hell out of me. That's why we're doing it. So, what does this look like? What does this look like? No more sloppiness here. What's it look like? It equals 0 when x equals 2. And when x is 3, where is it? 6 minus 4 is 2, right? So 3, 2. Is that okay? And then when x equals 1, where are we at? 2 times 1 is 2, minus 4 is negative 2, so we're up here. Okay. And so what are the slopes of this line? This is the point 2, 0, is that right? And what's this point here? This is 1, 1, 2. Plug in 1. I think you get 2 right here. And this is 3, 2, right? Okay, so the slope of this line is 2, right? What's the slope of this line? Negative 2? Right? All right, so now all we have to do is find the y-intercepts. Well, this isn't so hard. At least I don't think it's so hard. Let's see. Plug in 0 here. That's going to tell us the one y-intercept, isn't it? The 0, minus 4, that's positive 4. Oh, so the y-intercept is at minus 4. Is that correct? Thank you. Positive 4. And let's see. This is 2, and then we go over to, it's symmetric. Oh, no, but it's going to be down here. And so the y-intercept's going to be at, is it going to be at negative 4, isn't that right? Yeah, negative 4. Okay, so now, geez, Bart, so embarrassing. So now we do the integral from minus 4 to 2, because we want to see where the function's 0. Right? That's where the sign's going to change. You guys agree with me here? I'm going to take this line. So I'm going to integrate this line. And this line is minus 2x plus 4 dx. That's this line. Plus the integral from, oh, we're just going to the 1. I'm sorry. I'm out of it, but there we go. Are we good now? Yeah. So now let's do it. Equals what? Minus x squared plus 4x, all evaluated from minus 4 to 1. Right? This whole thing is equal to minus 1 squared, which is equal to 1. No, it's minus 1 squared. 1 plus, uh-oh, are we going to get negative? Or I don't know what's going to happen. Who knows what's going to happen? Isn't this 4 supposed to be a minus? So what we did was, first we tried to reason about this, right? But the issue was that we were accidentally reasoning about 2x minus 4 rather than the absolute value on the outside. And so to protect ourselves, we decided to take it down a notch and plot it, right? And when we plotted it, we realized that it's just going to look like this v thing, okay? But what's going to happen here is we're going to be, our v is going to be over here. And so here, it just looks like this line. And so we found the formula for that line, and then we can integrate that line just fine. It's this line on all the way to negative 4. That's correct, isn't it? Let's go ahead and, you know what? If we don't believe it, we just check. So what's negative 4 times 2? 8, negative 8, right? Negative 8 minus 4 is negative 12, so we get 12 out. What's negative 4 times negative 2? 8 plus 4 is 12, right? Okay, so we're doing fine. It all makes sense. Okay, so now we're going to have minus 1 squared here plus 4 times 1 minus the quantity. And now we're going to put in minus 4 squared plus negative 16. What's going to happen to all those minus signs there? They're going to become positive signs, right? And so we're going to get equals minus 1 plus 4 plus 16, plus 16. There we go. And there is our area. All right. Questions about this? You have a question? please. This is a negative x. This is outside. That's outside the squared. We're not squaring the negative sign. Did I answer your question? Sorry, go ahead. That's why it's -1. Yeah. All right. Let's do some accumulation function problems. Let's do all of these if we can. And then we'll be done. Okay, so my favorite questions from this sort of chapter are the following. Compute the derivative of f of x, capital F of x, where capital F of x is equal to the integral from 1 to x of, say, t squared minus 3t dt. Now, this might look like a hard problem when you first glance at it, but is this problem hard? What's the answer? This is right here? It's a 1. Right here? No, because the variable is x here. Yeah, that's a good question. He says, do you mean f of t? No, because the variable is up here in the limit of integration. And this guy says, hey, look at the fundamental theorem of calculus. This says that the derivative is just the thing on the inside here. So this is an easy question. This is, I wouldn't be surprised if you see this on your homework though, but t squared minus, sorry, it's x squared. X squared minus 3x is the answer. Now, did we do any calculation here? Nope, no calculation had to be done. Now, we're going to make the problem slightly harder. Ever so slightly harder. Okay, so here we go. What if I say capital F of x equals the integral from 1 to x squared, from 1 to x squared of t squared minus 3t dt. Now here, there's a very logical way to proceed, all right? And that would be, hey, I can compute. We'll do it. We can do it. This is a very reasonable way to proceed. It's going to give us the correct answer, all right? So let's do it. So what we could do is we could just compute this antiderivative. We're strong enough that we can do this. And so we're going to get that this equals, well, what's the antiderivative of t squared? Yeah, t cubed over 3. And what's the antiderivative of minus 3t? Well, it's minus 3 over 2 t squared, right? And then we could just evaluate this from 1 to x squared. Plug this in. This is going to be, should put parentheses here. This is going to be then x to the, oh geez, think about this. This is x squared cubed. That's x to the 6th. X to the 6th over 3 minus 3 halves times t to the, well, it's going to be x to the 4th, but yeah, x to the 4th minus, now we plug in 1 here, 1/3 minus 3 halves. It's 1/3 minus 3 halves. This is going to equal, it doesn't matter what it is, because what are we doing next to it? What are we trying to do? We're trying to compute the derivative. What's the derivative of a constant? 0. So now the derivative is, take the derivative here, it's going to be x to the 5th. It's going to be 2x to the 5th because the 6 is going to come down, the 3's will cancel, right? 2x to the 5th minus 6x cubed. 2x to the 5th, 2x to the 5th minus 6x cubed, when I take the derivative of this. This is a fine way. Oh, can you not read my beautiful handwriting? No, please. Which one can't you read? I'll just rewrite it. 2x to the 5th minus 6x cubed. This method's fine if you can compute the antiderivative of this. But it may be the case that you can't. So let me show you how to do it if you can't. There's a trick. It's not too hard. What you do is you just refuse to take the antiderivative. You say, well, this thing here, just call it f of x. And now, what's the fundamental theorem of calculus say? It says that f prime of x is equal to, well, it says that we can do that, but let's use the fundamental theorem version 2. So it says this. It says that the antiderivative, the integral from 1 to x squared of what, t squared minus 3t dt is equal to f. I don't know what this is, but it's equal to some, let's call it g. I'm sorry. G, where g is the antiderivative of this, of t, evaluated from 1 to x squared. Which is equal to g of x squared minus g of 1. G is the antiderivative of t squared minus 3t. And what do we want to do? We want to compute the derivative of this thing, right? So I compute the derivative of this. I say, well, compute d over dx of g of x squared minus g of 1. What type of thing is g of 1? It's a number, so its derivative is going to be 0. What's the derivative of this thing? Well, it's going to be, if I just use the chain rule, it's going to be g prime of x squared times 2x, isn't it? What's the derivative of g? It's equal to this. So this thing's equal to, I plug x squared in here, it's going to be x to the 4th minus 3x squared times 2x. Is this equal to this right here? It'd be kind of amusing if it wasn't, you know. No, like, is this your card? No. Yeah, these are equal, right? These are equal here. So let's do the real problem. So this is sort of the baby problem, getting us ready for the real problem. Here's the real problem, and then we'll be done. We'll just do this one problem, and we'll be totally done for today. That's what I say. Here we go. Last problem for today. One of my favorite problems. Here we go. So the integral from 1 to x squared of e to the t squared dt. Here's the deal. You cannot anti-differentiate this. All right? You can try, but you will fail. There is no formula that we can write down with a finite number of terms whose answer is this when you take its derivative. Nevertheless, I can compute this thing. What I do is I say, I can compute I can compute, if I know this, I can compute the derivative of this. So how am I going to do it? Well, I'm going to say, suppose g prime of t is equal to e to the t squared. Suppose I do have such an antiderivative. It's not that it doesn't exist, it's you just can't write it down. Yeah, that's weird. You know, we don't have symbols to write it down. Well, we have symbols, but the symbols that we use to write it down are exactly the integral sign. So that doesn't really help. All right, so now, here we go. So I suppose g prime is this. By the fundamental theorem of calculus, the integral from 1 to x squared of e to the t squared dt is equal to g of t evaluated from 1 to x squared. Right? Plug it in. G of x squared minus g of 1. Now, what sort of thing is g of 1 here? It's a constant. So now when I take this thing's derivative, so d over dx of g of x squared, I only need to work, this thing's going to be 0. By the chain rule, there'll be g prime of x squared times 2x again. Well, do I know the derivative of g? Yeah, I do. It's equal to e to the x to the fourth times 2x. So even though I could not compute this thing, I mean, we can still get around it and solve problems like this. All right, so we're done for today.